In the previous video, we introduced another powerful proof method called induction. And next, I'll introduce another form of induction called strong induction. Here is the rule for strong induction. Let P be a predicate on positive integers. And if the following statements are both true, then we can conclude Pn is true for all positive integers. The first one is P1 is true. Here 1 does not necessarily mean the positive integer 1. It means the first element that has this property P. The second statement is for all K, P1 and P2 and P3 and through Pk together imply Pk plus 1 is true. As a comparison, here is the second statement for induction. And if you compare them, you can see the difference lies in the hypothesis of the implication. For induction, we prove that Pk implies Pk plus 1. But here, we have more premises in the hypothesis. Instead of just the previous element K having property P, now we assume all the previous elements from the first one to the immediate previous one K, they all have this property P. And now we have more assumptions to use to prove that K plus 1 also has this property P, or in other words, Pk plus 1 is true. This is the reason why we call this one strong induction, because we have more assumptions to use to prove Pk plus 1 is true. Next, let's see two examples. The first one is we need to prove every integer n greater than 1 is either a prime or a product of primes. And at the very beginning of the proof, we state our game plan that we are going to prove this statement to be true using strong induction. And we still can use the template for proof by induction. The first step is basis step. And in the basis step, we need to prove that the first element in the domain has this property. In this case, the first integer, which is greater than or equal to 1, is either prime or a product of primes. And here you can see the smallest integer that is greater than 1 is 2. And we all know that 2 is prime. Next is inductive step. And in the inductive step, we first state the inductive hypothesis, which is assume for any K, the statement is true for any integer R, such that R is between 2 and K. In other words, R is either prime or a product of primes. And next, we state what we want to prove to be true. Show that K plus 1 is prime or a product of primes. And next, we're going to prove it. How should we proceed? Remember, we need to keep in mind we are going to use the inductive hypothesis, which says any integer R in this range is a prime or a product of primes. And you can see in order to use the inductive hypothesis, we should be able to represent K plus 1 using some numbers within this range. But how can we do that? We are going to use one of the basic proof methods we learned before, which is proof by cases. Since K plus 1 is an integer, we know that it must be either a composite number or a prime. So there are two cases. If K plus 1 is prime, then we are done with the proof. Second, if k plus 1 is composite, then what that means is there are other factors besides 1 and k plus 1 itself. In other words, k plus 1 is equal to a times b, where a and b are both between 1 and k plus 1, because they are two factors of k plus 1 other than 1 and k plus 1. And also because a and b are integers, these two inequalities are equivalent to a is greater than or equal to 2, less than or equal to k, and b is also greater than or equal to 2 and less than or equal to k. Now look, a and b are both within this range. Therefore, by the inductive hypothesis, we can conclude that both a and b are either primes or a product of primes. And therefore, you prove that k plus 1 is a product of primes. And that's the inductive step. Now, combining the basic step and the inductive step, we proved the original statement is true. Second example, we want to prove that any amount of postage greater than or equal to 8 cents can be built using only 3-cent and 5-cent stamps. Mathematically, this statement means that any integer n greater than or equal to 8, n can be represented by a summation of multiple of 3s and a multiple of 5s. We're going to prove this statement with two different ways of using strong inductions. Here is the first one. In the basic step, we need to prove that this statement is true for the base case. In other words, this statement is true for the smallest amount of postage that is greater than or equal to 8. And in this example, we need to show 8 is equal to 3 plus 5. For the inductive step, we first state the inductive hypothesis, which is we assume for any integer k greater than or equal to 8, and for any integer r that is between 8 and k, r is equal to the summation of 3s and 5s. This is our inductive hypothesis. Next, we state we need to show that k plus 1 is also equal to the summation of 3s and 5s. How do we show that? If we can represent k plus 1 using a number of small values, then we can apply the inductive hypothesis to show that k plus 1 is equal to the summation of 3s and 5s. And to do that, we're going to use this trick. We're going to subtract a 2, then add a 2 back into this k plus 1 to make sure the equation still holds. Then this is equal to k minus 2 plus 3. And if we can show k minus 2 is within this range between 8 and k, then we can conclude k minus 2 is a summation of 3s and 5s due to the inductive hypothesis. Then since you add another 3, of course you can conclude k plus 1 is equal to the summation of 3s and 5s. But can we guarantee that k minus 2 is within this range? Let's check. First, it's obvious that k minus 2 is less than k, so this side is fine. However, can we guarantee k minus 2 is greater than or equal to 8? No, we cannot, because we only assume that k is greater than or equal to 8. But now let's see how we can make sure k minus 2 is greater than or equal to 8. So let's derive the value of k. K must be greater than or equal to 10. And therefore, k plus 1 must be greater than or equal to 11. Therefore, as long as k plus 1 is greater than or equal to 11, this technique we used previously is valid. However, if we do so, there'll be a gap between 8 and 11, which are the integers that we haven't proved that can be represented by the summation of 3s and 5s. So in order to fill this gap, we're going to use one of the basic proof techniques learned previously, proof by cases. So we divide the values of k plus 1 into 3 cases. One is k plus 1 is equal to 9. A second one is k plus 1 is equal to 10. Then third case is k plus 1 is greater than or equal to 11. For this case, 9 is equal to 3 plus 3 plus 3. So 9 can be represented by the summation of 3s. 10 equals 5 plus 5. So 10 can be represented by summation of 5s. Now, this is the complete inductive step. Combining these two steps, we proved the original statement is true. In this method, you can see we have to discuss the value of k plus 1 case by case. But can we avoid doing this? And in the second method, we're going to see how we can avoid proof by cases for the inductive step by adding more base cases in the basis step. In the second method, we still apply proof by strong induction. But difference is now, in the basis step, we not only prove 8 can be represented by the summation of 3s and 5s, but also we add 2 more base cases. 9 is equal to 3 plus 3 plus 3, and 10 is equal to 5 plus 5. Now, in the inductive step, we only need to show for any integer k that is greater than or equal to 10, which is the last base case we proved in the basis step, such that for any integer r between 8 and k, r can be represented by the summation of 3s and 5s. That's our inductive hypothesis. Same as the previous method, we need to show that k plus 1 is equal to the summation of 3s and 5s. Now we can directly use the previous technique. We first subtract 2, then add a 2 back to make sure the equation still holds. Now we can represent k plus 1 by k minus 2 plus 3. And now, since k is greater than or equal to 10, k minus 2 is greater than or equal to 8. And now you can see k minus 2 is obviously within this range. So you can conclude k minus 2 is equal to a summation of 3s and 5s. And since you add another 3, of course, you can conclude k plus 1 is equal to a summation of 3s and 5s. So now you look at these two different methods. The point here is, depending on the problem, sometimes it may be necessary to add more base cases in the basis step in order to make the proof of the inductive step easier. Now we have talked about both induction and strong induction. Let's see what the relation is between these two inductions. First of all, induction applies when the information about one position back is enough for the inductive step, then you can apply induction. And strong induction applies when you cannot directly prove that pk plus 1 is true just using pk is true. If it's easier to prove pk plus 1 is true using all the previous elements in the domain, then you should consider using strong induction. Next, I want to ask you an interesting question. Is strong induction stronger than induction? By stronger, what I mean is, can you apply strong induction whenever you can apply induction, but not vice versa? It's obvious to see that whenever you can apply induction, you can always apply strong induction. Because if you can prove pk plus 1 is true by using just pk is true, of course, you can prove pk plus 1 is true using not only pk is true, but also all the elements before k. But what about the other direction? Is that true that you cannot apply induction when you need to apply strong induction? The answer to this question is no. Actually, these two inductions are equivalent. In other words, theoretically, you should be able to use either of these two inductions for a proof. And the proof for this equivalence relation between these two inductions is quite involved. I will not talk about that in this class. If you are interested, you can search on Google. Finally, here is an exercise I strongly encourage you to work on after you watch this video, because the property here is not about integers anymore, as we did for the examples. Instead, it's about a sequence of values which are defined by this part and this part. So here, the integers are just used as indices of the values in this array.